This is technically the third session of our little classes that we hold, but we're gonna go over the first session real quickly, um, so people get caught up um, with everything. No, the entire screen. Okay, so we um, we kind of we kind of left off around page 12, I believe. Yes, page 12. Yeah, we finished page 12 last week, but let's just go over the questions real quick from the beginning. So, since there were some people who weren't here on the second one, so we can go over that real quick too. Um, what we are following is the no nonsense technician class study guide. All right, and links to all of that is in the chat groups. All right. Um, we were going over some basic electrical principles last week. Um, what is voltage? What is the electrical term for the force that causes the electrons to flow? That's of course is voltage. The name of the what is the name of the flow of electrons in an electrical circuit? That's current. And electrical current is measured in which of the flowing units? That's amperes. Actually, guys, before I even continue with this, I want to show you guys one thing real quick, um, which is this little, which is this little channel on YouTube. If you Google this channel, I've already sent out the links to the playlist on this channel. This guy gives a great detailed lectures on everything that we're talking about. So the link to this actual playlist is on our chat. Okay, I would really suggest in between throughout the week you kind of listen to all of these videos. For the technician class, there's what, 17? Yeah, there's 17 videos on the technician class, and you can see, hour and 15, hour and 42, hour and a half, hour and 40. There's some in here that's almost 2 hours long. Yeah, 2 hours long. So this is a very good um, playlist to look at and kind of study with along with. So we're just this is the exact book that he follows. So we're just gonna be going over the questions and answers real quickly. Since we only have about an hour or so a week, more like about 45 minutes or so, 45 50 minutes. That's about all we really got. So we don't have time to go into all the details and ins and outs of every single thing that's talked about. So we're basically going over the questions real quickly, and then at the end having a little question and answer session to help you guys out a little bit. Which of the following describes an alternating current, an AC alternating current, current that alternates between positive and negative. So, an alternate, you're alternating. Sometimes you will have like little good clues, and sometimes they're going to be deceptive. All right. So if you look at the word alternating here, that kind of shows up in all three of these answers. So just kind of be careful, about be careful in reading everything, and alternating something between means like going back and forth between something. So alternating between positive and negative. In the first answer here, it's only positive is mentioned. The second question answer is only negative is mentioned. Only the third answer here is both positive and negative are mentioned. So just be careful about the way they word the questions and the answers. The other thing I wanted to also mention quickly, this ABCD, the pattern, the order that these answers are in, they're going to change on every single question, every single test. These are going to change. So please don't remember A, B, C, or D. Please remember the actual answer. Okay. So what describes the number of times per second in alternating current makes a complete cycle. Up here, it is talking about a whole cycle of an AC current, an alternating current. So what describes it? It's the frequency. All right. And how do you measure a frequency? It's in hertz. You measure frequency in hertz. All right. Then we go into Ohm's law. What are the units of electrical resistance? How do you measure resistance in a current? In alternating current, we're talking about right now. So it's called ohms. Ohms. All right. So right here is the symbol for ohms. You're gonna come across that a lot in your ham radio career. So remember that little symbol there. It stands for ohms. All right. So what type of current flows in the opposite is opposed by resistance? What type of current flow is opposed by resistance? All of the above. The DC current is opposed by resistance. The AC current, alternating current, is also, and the radio frequency current is also opposed by resistance. Resistance, just means that something resisting against something. So everything is affected by resistance. All right. What metals are generally good conductors? What conductors of electricity? What metals electricity can pass through? They have many. Why are metal? I'm sorry. Why are metals generally good for conductors in electricity? Because electricity can pass through it, and in order for electricity to pass through something, it needs a little bit of free space in between the make of the material. So they have a lot of free electrons going, making up the metals. That's why they're good conductors. So what is a insulator? A good insulator. So the opposite of a conductor. The greatest insulator is glass. Okay. If you look at the other, copper, electricity, all of our wirings in our house is made out of copper. Okay. Aluminum, of course, is a very good metal to conduct electricity also. All right. And mercury is a liquid metal. So it's kind of a metal. So it's a very good conductor of electricity. So they're looking for something that is an insulator. That is the opposite of a conductor. All right. That is glass. All right. So Ohm's law. Ohm's law basically is E equals I times R. All right. E is voltage. Voltage is described by the letter E. R is resistance. All right. and current is I. So E equals I times R is the formula for Ohm's law, which is the first question here. The formula that is used to calculate voltage in a circuit, E equals I times R. There are some great YouTube videos on explaining Ohm's law. I would suggest searching them up. Great YouTube videos. So the formula. So if you know, I or if you know R, you can calculate for E. But if you know E and you know I, you know, it's basic math. You just kind of flip the numbers around. If you know if you want to know the resistance, you would take E and you divide it by I. Okay. If you want to know the I, you would take the E and you would divide it by the R. All right. So it's just basic, simple math. Little bit of not too much in algebra, but just basic algebraic knowledge is always good. In here they're solving for I, so they're taking the E and dividing it by R. All right. So some examples of Ohm's law. So if you got a circuit with a 3 amp current and you connect it to 90 volts, what's going to be the resistance? Okay, so you would take your 90 and you would divide it by 3. You take your 90 and you divide it by 3 and you get 30. All right, and here they're asking for resistance. All right, so what you would take your 12 volts and you would divide it by the 1.5 amps and you would get 8 ohms. And next one is they're looking for resistance again, and 12 volts. You got 12 volts and you got 4 amps, so you would take your 12 volts divided by 4 and you get 3 ohms. Next one is we're looking for I, and you got 120 volts and you got 80 amps. So 120 divided by 80, you got 1.5 amps. And you will not have access to a calculator. You will not be able to touch your phone while you're taking these tests. So it's really good to kind of understand how Ohm's law works. Okay, this little paragraph here. All right. And how to solve for each of how to solve for E, how to solve for I, how to solve for R. It's good to know all these things, because you're not gonna have a calculator in front of you, or you can just blind memorize it. That works too. So the next one, T5D08 is gonna be you're solving for I. And you got your 200 volts and you got your 100 ohms. You take your 200 divided by 100, you get 2 amps. All right. 24 ohm resistor connected across at 240 volts. So 240 volts divided by 24 and you would get 10 amps. All right. We got same questions over and over again. How to go about solving for E, how to go about solving for I, how to go about solving for R. Just real quick, 0.5 amps times 2, you get 1 volt. All right. Again, same thing here. E equals I times R. So 1 amp times your 10 ohms equals to 10 volts. All right. Same question again. You got your 2 amps, and it's flowing through. You got your 10 ohms. I'm sorry, and it's flowing through a 2 amp current. So you would take your 2 amps, times it by 10, and you would get 20 volts. All right, series and parallel circuits, and in which type of circuit is DC current the same all throughout the components? That's a series circuit. It's all in one series. Okay. Parallel circuits, I believe we're talking about next. Which circuit is voltage is same across all components? The voltage is the same across all components, and that would be parallel. All right. DC power, going into DC. Which term describes the rate at which electrical energy is used? Of course, that is power. All right. Power is the rate at which electrical energy is generated or used. Power is measured in watts. All right. And we use the letter P to stand for power and W to stand for watts. All right. So what describes the energies that is used? Electrical energy that is used, that is power. Electrical power is measured in which of the following units? Measurement of power is watts. Watts. Some more calculations, some more formulas. To calculate power, we multiply the voltage across a circuit by the current flowing through the circuit. So P equals E times I. All right. Which formula is used to calculate electrical power P in a DC circuit? P equals E times I. Some examples. So we got 13 volts of DC and a current of 10 amps. 13.8 times 10 will give you 138 watts of energy coming out of this particular example. All right, how much power is delivered by a voltage of 12 volts DC and a current of 2.5 amperes, 2.5 amps. So you would take your 12 volts, times it by 2.5, and you would get 30 watts. 30 watts. All right. So in here, we're kind of just flipping what we're looking for. We're looking for I this time. All right. So I equals P times E. And we got 120 watts at a voltage of 12 volts DC. So 120 watts divided by 12 is going to give you 10 amps. And you'll come across these kinds of questions a lot in the test. Some examples of what a milli, what a micro is, what a pico, what they mean by pico and kilo and mega, and all the different terminologies that we use in radio and in electrical concepts. So you guys can, it's pretty self-explanatory, just kind of look over that real quick. So how many milliamps is 1.5 amperes? So milliamp is like millionth of an amp. So you got 1500 milliamps in a 1.5 amps, in 1.5 amps. All right. What is equal to 1.5 million hertz? 1.5 million hertz is 1500 kilohertz. And to convert from hertz to kilohertz, you divide it by 1,000. which is equal to 1 kilovolt. 1 kilovolt. Kilo being the operative word here. Kilo means 1,000. So that's 1,000 volts here, which is equal to 1 microvolt. Microvolt. That is 1/1 millionth of a volt. Very, very little bit of energy. Tiny, tiny little bit. So to convert from kilovolts, you multiply by 1,000. To convert from microvolts, you would divide by 1 million. So which is equal to 500 milliwatts. 500 milliwatts, 0.5 watts. 0.5 watts. That is, if I'm not mistaken, that is the amount of power our little Bofeng radios that we use at our masjids to communicate, that have the, I think, like 7 or 9 channels that normally, the smaller mosques use. I'm sure we still use them. So that's about 0.5 watts is about the amount of power that our little Bofeng radios use. To convert from milliwatts to watts, you would divide by 1,000. So 500 divided by 1,000 would be half, or 0.5, which stop. Okay, which is equal to 300 milliamperes. 300 milliamperes, 3 amps. All right. There are 1,000 milliamps in an amp. So to convert from milliamperes to amperes, you would divide by 1,000. Divide by 1,000, which is the abbreviation for kilohertz. Kilohertz. All right. Please, smaller case K, capital H, smaller case Z. All right. None of these other ones are correct. Please don't do that. Some people out there in the radio, in the ham radio world, will get really, really pissed off if you write it that way. I've actually been yelled at because I made a mistake, and I wrote it. I think I wrote it in all caps one time on one of the emails that I sent, and one of the guys messaged me. He's like, "What are you doing, man? Write it the right way." Okay, I'm sorry. You're right, though. But yeah, please, lowercase k, capital case, capital H, lowercase z. All right. So 1 kilohertz is 1,000 hertz, or 1,000 cycles per second. Note that the H in hertz is capitalized. All right. Very important. H is capitalized. 1 million cycles per second is 1,000 kilohertz, or 1 megahertz. All right. Now here, the M is also capitalized. All right. So that's where they're going to try to trick you in the next question here. What is the abbreviation for a megahertz? So that is capital M, capital H, lowercase z. And you will notice in the ham industry that we refer to Z's as Z. It really doesn't have anything to do with, Z is the British pronunciation. It has nothing to do with that. It's because Z kind of sounds a lot like C or D or T or P. So we kind of stick to calling Z Z because it separates it from all the other similar sounding letters. All right. So kind of get used to that. Also calling Z's Z. All right. Which is equal to 3.525 megahertz. 3.525 megahertz. All right. So again, 3525 kilohertz. So going from megahertz, where was this? Going from it's just 1,000. 1,000. 1 kilohertz is 1,000 hertz. All right. So you would basically multiply that, move the decimal point over one, and you get your kilohertz, which is equal to 28,400 kilohertz. Move the decimal point over two spaces, and you get 28.4 megahertz, which is equal to 2425 megahertz. Move the decimal place over once, and you would get gigahertz. So just kind of look over, where was that little table? This little table right here. Okay, when you get a few moments, please look over this little table. It's very, very handy. Okay, this will explain pretty much this whole entire section to you in detail. So to convert from megahertz to kilohertz, you would you would multiply by 1,000 to convert from kilohertz to megahertz, or to convert from megahertz to gigahertz, you would divide by 1,000. So which is equal to 1 million picofarads. 1 microfarad. Again, all the picos and the micros are all described in this little table right here, along with all the technical how you would write it and everything. All right, the lowercase p, the lowercase n, they all matter. So where were we? Picofarads. A million picofarads is 1 microfarad. All right. Decibels. You're going to come across a lot of instances, especially when you're looking into antennas, that, hey, this antenna will boost your this antenna has a 3 dB gain, or a 6 dB gain, or a 10 dB gain. There are two types of dBs, which we will get into later, but right now let's just there's dBi and dBd. We're not going to get into what I and D is at the end right now. We'll get into that later on. I think when we get to the general portion of the class. But decibel, especially when dealing with the ratio, especially power ratios, we often use decibels. Okay. The reason for this is that the decibel scale is a logarithmic scale, meaning that we can talk about large ratios with relatively small numbers. When the value is positive, it means that there is power increase. You will come across instances where you're getting a negative decibel gain on a particular antenna, which is not good in certain points, but it's not that bad either. Okay. It really shouldn't discourage you from purchasing an antenna if you see a negative decibel gain on it, because believe it or not, just about every single antenna that is out there is going to have a negative decibel gain in one direction or another. They all do. So when the value is positive, it means that it has a power increase. When the value is negative, that means that it has a decrease in power. Okay, so at this point, you don't need to know the formula for calculating. Of course, you don't. It gets very, very complicated. But you need to know the ratios represented by the values 3, 6, and 10 dBs. Those are 3, 6, and 10 are very important numbers in as far as decibels go. So you'll see that in just a minute. Which decibel value most closely represents a power increase from 5 to 10 watts? So you're basically doubling your power there. So when you double your power, you gain about 3 decibels of power in the amount of radio frequencies that is transmitted from your antenna. So when an antenna says that it has a 3 decibel gain, it basically will turn, let's say, a 50-watt radio into a 100-watt radio. Okay, that is a very good thing. 3 decibel dB corresponds to a ratio of 2 to 1, and because it's going from 5 to 10, it doubles the power. We can also say that there is a 3 dB gain. Exactly what I said. You're basically doubling your power. With a 3 dB gain, you're basically doubling your power. All right. Which decibel value most closely represents a decrease from 12 to 3 watts. 12 to 3 watts. Okay? That's a negative 6 decibel loss, or a negative 6 decibel gain, or a 6 decibel loss. Whichever way you want to look at it, they're both saying the same thing. So you got a 12 watt radio, but you're only putting out 3 watts. So half of 12 is 6, and half of 6 is 3. Okay, remember we said when you double your power, when you got a 3 dB gain, you doubled your power. So if you got a 3 dB loss, you lost half of your power. Okay, so you're halving your power twice, going from 12 watts to 3 watts. All right, down to 6 and then down to 3. So a 6 dB corresponds to a ratio of 4 to 1 and decreased power from 12 to 3 watts. Okay, because the power decrease value is negative. All right, so which decibel value represents a power increase from 20 to 200? 20 to 200. That's a 10 decibel gain. 10 decibel gain. Increase of power from 20 to 200 is a ratio of 10 to 1. And a 10 decibel corresponds to a ratio of 10 to 1. So, electronic components and circuits. So we're talking about resistors in the first section here. What electrical components opposes the flow of current in a DC circuit? What electrical component opposes the flow of current in a DC circuit? Opposes. It kind of hinders it. All right. So resistors oppose the flow of a current in a DC circuit. What type of a component is often used as an adjustable volume control? The little volume control on your radios and stuff. That is actually, the term for it is potentiometer. Okay. What electrical parameter is controlled by a potentiometer, it's resistance. So when you're turning the volume knob on your radio, it's increasing and decreasing the resistance in that DC circuit inside your radio to make it louder and quieter. Okay? Capacitors. Another common electrical component is a capacitor. The most basic capacitor consists of two metal plates separated by an insulator called a dielectric. When you put a DC voltage across a capacitor, the electric current flows into the capacitor until the voltage across the capacitor equals the DC voltage. This puts a positive charge on a plate and a negative charge on the other, thereby creating an electrical field between the two plates. What type of electrical component consists of conductive surfaces separated by an insulator? A capacitor. Okay. What electrical component stores energy in an electrical field? That is a capacitor again. Capacitor stores energy in an electrical field. In that electric field, the ability to store energy in an electric field is called capacitance, and the unit of capacitance is called a farad. Farad. All right. What describes the ability to store energy in an electric field? Of course, is the capacitance. And how do you measure capacitance? Is by farad. Farad. Inductors. Third most common component, amateur radio equipment, is an inductor. Inductors are usually small coil of wire, and when when a current flows through the coil of wire, a magnetic field is set up around the coil. I don't have a I don't have an inductor around me. No, I do not. Wish I could show you guys an example of an inductor right now. Okay, maybe next time. Maybe I'll throw some in the chat. All right, what electrical component is typically constructed as a coil of wire? Coil of wire is an inductor. What type of electrical component stores energy in a magnetic field? That's an inductor again. You're not going to see all these questions again. There are I think like around 412 questions in the technician class, and you will only see 35 of them. So that's why you will see right now, as we're going through them, you're going to come across, multiple questions asking the same exact thing, just a different way of them wording it. All right. So don't worry, you're not going to see the whole, every single question that you see here. What type of electrical component stores energy in a magnetic field? That's an inductor again. Again, the inductor stores energy, and the ability to do so is called the inductance. And the unit of inductance is Henry. Henry. So describe what describes the ability to store energy in a magnetic field is an inductance. Inductance. All right. And how do you measure inductance? Is by Henrys. Henry. All right. Batteries, which is, very, very good thing. I need to have batteries. We all need to have batteries for all kinds of things. You got your a lot of different kinds of batteries, nickel plated, nickel metal hydride, lithium ion, lead acid, and then of course your rechargeables and all kinds of zinc batteries are out there. Um, so these batteries from here to here, your nickel, your lithium ion, and your lead acid, they are rechargeable batteries. All right. Um, the carbon zinc batteries are not. Like carbon zinc batteries would be like your the AA AAA batteries that you would buy from Walmart or something, Duracell, things like that. Um, those are not rechargeable. They do make the rechargeable ones, yes, but your normal everyday battery, of course, is not rechargeable. Um, the the lead acid batteries, they get a little dangerous. You got to be a lot more careful with them. Um, you don't want that acid spilling out. Okay. Um, so in ham radio world, we kind of try to stay away from the lead acid batteries as much as we can. And the nickel metal hydride batteries, they're not that common at all in our industry, in our world. Lithium ion is what we normally live and die by. Um, they are very versatile, very safe, very long lasting batteries, and they are rechargeable, and you can recharge them from solar panels, from your outlets at your home, from a generator, whatever. They're very flexible batteries, and they hold the charge a lot longer than any of the other batteries out there in the world, and very, very safe also. So, which of the following battery chemistries are rechargeable? Rechargeable, of course, we were just talking about the three kind: the nickel, the lithium ion, and the lead acid. They're all rechargeable. Of course, they are. They're not as safe as lithium ion, but they are rechargeable. They definitely are. There's no doubt about that. Which of the following battery chemistries are not rechargeable? Not rechargeable. The carbon zinc, your Duracells, all right, are not rechargeables.